Up to this point, we have assumed that we have a notion of phrase structure available. So for example, the derivational search function, there we simply assume that we have a grammatical operations that can create and modify phrase structure representations. But before we can actually run or test anything or work with the linguistic materials or data sets, we need to have first a theory of phrase structure, some kind of idea of what it is that the brain is creating when it's understanding and producing language-related behaviors. And that's the empirical part. Then we also have to have an implementation. The derivational search function will not work if we don't have a phrase structure representations defined somewhere in the actual code. And so in this presentation, I will be briefly looking at how we can implement something like this. And because the phrase structure itself is a controversial topic, there is no agreement on what it is and how we should approach it. I will not pay so much attention to those empirical questions. Rather, my idea is to try to give some guidelines on how we can approach the implementation. So let's go directly into the topic then. It's my view that whatever theory we have of the phrase structure, it's best to begin from the assumption that it is defined in its own class and its own module. And this is because even if we could use, if some theories of phrase structure could potentially use Python or other programming languages data structures directly for implementation, we don't know in advance what properties we will need. And also keep in mind that the supervision layer will also sometimes and often impose its own requirements for bookkeeping. For example, we might want to follow a number, the constituents, and keep track of the transformations, their inputs and outputs, etc. So often it happens that even if the empirical part of the theory is simple, the actual phrase structures will have properties that some properties that are irrelevant to the empirical part, but are part of the whole computational infrastructure. So we start from a phrase structure class and module. Now, I just want to comment briefly what a class and module is. A class is a blueprint. It's a blueprint of an object which lives inside of the program, the source code. And the object can have properties which define what type of object it is, and then we can define functions which define in which way it can behave, how it can manipulate its own properties and data. And so the phrase structure class likewise will be a blueprint, a definition of what kind of properties the phrase structures have. And then we will have functions inside of the same class which define its properties. And I will also show how we can create, and actually I recommend that we create always an abstraction layer. We can create more complex properties by combining the more primitive ones logically with each other. So, but I show what this means. So, and then this object, then during the runtime when we execute the program, we will then take this class or the blueprint and create objects, individual data objects, which are incarnations or instantiations or tokens of this class. So the class in this case defines what the phrase structure objects are, and then when we run the program, we create this type of objects, which are the actual linguistic representations that the derivational search function, for example, manipulates when it is deriving sentences. So we make a distinction between the class and its objects. And here is a simple definition, class definition for phrase structures. This is from the template 2.2 in my templates project, as all other scripts that we have looked so far. So we just begin by declaring that now we are defining what the phrase structures are. And then here we have a function whose name has to be always, in Python, it has to be this init with the two underlines before and after. So now Python knows that this is a special function. And this function is something that we call and execute always when the objects are created, when our program is creating the actual phrase structure objects that are going to be manipulated. And inside of this function, we then tell what the properties of phrase structure objects are. And we can also, if we want, we can execute operations already here. If we want that some behaviors are always executed when these things are created, but here we are really not doing that. And so what I'm doing here is, first we have a phrase structure constituent can have its daughter constituents. And this is simply when we have imagined that we combine more primitive elements to complex elements. So this combination and the output is described here. So this complex phrase structure can have two daughter constituents, which are here represented by relying on ordered pair. This notation, this Python notation here is an ordered pair. So we have a x and y, and they are ordered in this precise way. We have a left and right asymmetry built into this theory of phrase structure. If you don't want to have asymmetric constituents, you would use, for example, set. So if we have a set of x and y, then the order will disappear. These daughter constituents, when I'm defining them here, I can simply later in the code, if I want, create constituents by providing this type of pairs for phrase structure objects, or I can modify the objects by changing the constituents. I have to change the whole pair, but that's irrelevant. But as you can see here, we can also provide the x and y as input arguments to the constructor, the init function. So this allows us to create complex phrase structures by providing the daughter constituents as inputs. And this is what I'm doing here. There's an example here. So if I say phrase structure, and then I give the x and y as arguments, this will return or create a phrase structure object, an object of this class, which will have x and y as daughter constituents. And that's exactly the assembly operation as I've been discussing so far. You can see that I have given it another name, merge, because of this reason. Now, all of this will depend on your view of what really the constituency structure is. If it's some kind of containment, so that the complex constituents contain, they are like containers, or if you think that the constituents relations have semantic interpretation, in that case you would not use ordered pairs, but you would perhaps use Python dictionaries or dictionary, another data structure. So the implementation here should closely approximate the empirical theory you have in mind. And of course, to do this, you need to know something about the primitive data structures that Python makes available. This is not the topic of this presentation. But I want to point out something important when we come to this point. Namely, it's not given. You can't assume that your theoretical idea of what the phrase structure is can be implemented in a simple way by using the default data structures that we have available in Python or whatever language you use. And ultimately, of course, the implementation is taking place in the human brain. So it's a neurophysiological system, not Python. And that's why this has to be thought as, in most cases, this stuff here cannot be considered literally as the theory. It has to be, we have to satisfy by assuming that this is a close approximation of the empirical ideas, as close as is possible in Python or whatever other medium we would use. So this ordered pair is as close approximation that Python can provide as possible, given some type of intuitive idea what the phrase structure is about. But it cannot be the real final truth, which must be some type of neurophysiological mechanism. So that should be mentioned here. Now I do want to mention one alternative possibility here that you might think or might consider, and this is something that I used myself in some earlier versions. Now, because my idea, my underlying theory of phrase structure is that this is asymmetric binary branching phrase structure. So originally, and this is another possibility we could consider, which is that we define the left and right constituent axiomatically, as I have done here. So they are separate, independent, autonomous properties of complex phrase structures, constituents. And this matches now perfectly with the idea that the phrase structures can be binary branching, and that we have left and right constituents available. Left and right is a heuristic term. It's not, of course, in the brain that it's left and right. It's more first and second, perhaps. It's a temporal asymmetry ultimately. But putting that aside, so this is an alternative. We can always give up using any Python default data structure and just define the properties axiomatically, as I have done here. But now I don't do this, and this is an example script, so we don't take this too seriously. Just to mention that option. So that is about what it is that we have a constituents in a phrase structure. What is it ultimately about? So we have this axiomatic approach, ordered pairs or tuples, or we have lists, dictionaries. These are the main data structures that Python will offer. Let's move on then. Then we have, I have here an independent property called feature, which is a set. And this set will hold lexical features for primitive constituents. And this is extremely complex question that I have not been able to thought out clearly or solve yet myself, but it's absolutely required that we have primitive constituents that have features. And those features have to come from the lexicon. And it's very difficult to do this theory unless we assume that the syntactic assembly operation can also manipulate these features. And so I have defined here features data structure as a set. But the problem is that now that it's part of this definition in this way, this will automatically generalize to all phrase structures, whether they are simple or complex. So now every phrase structure constituent, whether it's simple and from the lexicon or rather this complex one, will have a set of features. And these are always lexical features in my own model. So this is wrong if we want to have a really simple phrase structure where the complex elements are simply abstract combinations of their constituents and don't have their own independent features. And because I work with that type of phrase structure myself, what then happens is that this features property is never used for complex constituents. But still, because it's defined here, it is part of them. And that's wrong in my view. And I have an idea how this could be worked out. My idea is that the primitive constituents don't have actually lexical features, but they point to the lexicon where the actual features are. So then I don't have this then I don't need this field, but instead I have some link which brings the constituent into the lexicon, and that same link, kind of copy link, is what I will use in capturing transformations and other similar things. But it doesn't work so simply because if the derivations can change these features, so it's never the case that when we are producing sentences that we would go to change features in the lexicon. So that would be we have to take a copy from the lexical items, and then those we have to be linked to phrase structures that would have this set. So, but I'm not sure. I'm just mentioning this to show what type of problems we have when we are really going to the very, very detailed level in the implementation. So what this illustrates is again the situation that what I'm implementing here doesn't really match well with my intuition of what the empirical theory is, the theory that I'm trying to create here. It's just an example of the same problem. Then here I am just again for the sake of example, assuming that every constituent also have a pointer to its mother. So when we create daughter constituents, they will also know their mother. This is not necessary. It's a very fundamental assumption if it's true or not. And if you need this in your model, I need it in my empirical hypothesis, but it's not necessary. So if I remove this mother attribute from here, what will happen then is that every constituent can look downwards to its daughters, but the daughters really have no natural way of looking upwards. They don't know who their mother is unless we do an artificial search through all the constituents and find the daughter in that way. So in other words, from the external processes can see the motherhood, but the constituents themselves don't know that. But there are other things here. I'm assuming that every constituent can have only one mother. So there is a possible to craft or design a theory of phrase structure where every constituent has several mothers. And then I have a phonological exponent, which I don't recommend doing it this way. This was simply to create a simple example script. Because in more realistic theory, the phonological features could be here, or in some theories they are only part of the post-syntactic system, which means that we would have to have some type of how would I implement this? What would be the best way to do this? We would have to have like another lexicon which is accessed by the post-syntactic function, or the module that implements that would have access to this other lexicon from which we then would pick the phonological properties. So then, meaning that the syntactic derivation will not see anything related to phonology. But it's really, for the most part, it's really this, it doesn't matter. It comes into we need to have extremely complex and non-trivial data sets to show that one of the other theories right or wrong, simply because if I have the phonological feature in this set, it will just be there, but nothing is done with it. And then only in the post-syntactic operations, we pull out that feature. And in fact, we delete everything else because the ultimate sentence will just have phonological features and everything else will be wiped out. So let's put that aside. And so this is an extremely simple starting point and gives an idea, I hope, how would we do and start approaching this question. Now, when we have this representation, we create the data structures and its properties, then we need the functions which are doing something with these elements. For example, the assembly operation, as I have been already discussed many times. And I recommend that all these operations, whatever the context of use, will be part of the same class. So you can see here that I have defined the operation merge in this class, and also other functions that we have already discussed, like the preconditions. And here is the print function, which prints the phrase structures out. So all the things that are manipulations that you can do with phrase structures would be part of this class functions of the phrase structure class. And so now just go back to the assembly operation. Here what I'm doing is that I'm defining a function merge, which takes two arguments, x and y. And now a side comment for Python programmers. You can see that I don't use the self here. And that's bad Python, that would be the proper Python way to do it. But in my own programming, I always assume that all the phrase structures are capital letters. Everything else I use the self. So just a comment about this odd notation. But here, for everybody else, the merge takes these two phrase structures as input, the two elements that we are combining. And remember now the derivational search function in this script is calling this function when it's creating all the combinations. And then we create a complex phrase structure object, give this daughters x and y as inputs. They are here. And then they go into the object as constituents, daughter constituents, into this ordered pair. And we return the new phrase structure, what results, the new complex phrase structure node. And in the same way, we would apply all sorts of operations, whatever we have, move, agree, feature interface, case concord, everything would be added here, and it will manipulate in phrase structures that are given as input. And one more comment is that has to do with the abstraction. Abstraction means that we hide the actual implementation of the class or the objects from the external outside code. And so here, for example, I have defined two functions, left and right. And the left, let's look at these definitions first. A left constituent is the first constituent in this ordered pair, as I'm stating here. That is, we will call it now a left, because the function is named left. And right constituent is the second daughter constituent. So the constituents from this pair. 0 means first, it's an index, and y is the index 1, but it's the second element of the pair. And now the idea is that all the other code we write, where we, let's say, manipulate constituents, perform some manipulations like agreement, concord, movement, that when we are referring to the daughter constituents, we only use these functions, left and right, that as I'm defining here. So think of these functions as providing an interface. Imagine that the constituents are like a closed balls, for example. All the properties are inside. And then they have the constituents which are coming out of them. When the external code comes to look at these phrase structures and do something with them, for example, it wants to look what is inside the left constituent. Then it will always use this function, this interface function. This will define what the left constituent is for all the external code. And the consequence when we do it in this way is that the external code will not see that we have implemented these objects by using ordered pairs. All it sees is we have a left and right constituents. It doesn't touch this part. The only part of our program which is using this ordered pairs is this interface function here. And now what we get from it, we get two important things. One is that we can make this interface layer to match with our theoretical intuitions. So we actually hide the actual implementation and create this surface where we have properties that exist in our own empirical hypothesis or model or theory. The left and right, and not this ordered pair. And we are assuming that whatever we do under this interface layer, that's something that ultimately will have to be based on neurophysiology, neuronal architecture and neural processing, and not Python. So that's one thing where I find this extremely helpful. Also here, notice because this definition of merge is nearly trivial. I'm just saying that, what I'm saying here is that let us assume that when we create a new phrase structure by providing it with two daughter constituents, that is called merge. All I'm saying here is that. But I'm doing it because I want to assume that the theory has based on an operation like merge and not some kind of Python specific technical implementation of how new objects are created. So now for the outside code, it looks like that I'm also always doing merge, and it doesn't look like that I'm engaged in some type of manipulation of Python class. Okay, but then there is then we have a second reason. Now imagine if everywhere else in the code, let's say we have 25 other pieces of code, not here, but somewhere else in our computational infrastructure. Let's say, for example, where we draw the images, where we are manipulating or reading the constituents, the daughter constituents. Let's say 20, 30 times in other places in the code we are calling that, need this information. So if we then go back to the actual Python implementation of the daughter constituents, and we want to change something, let's say that we come to think that, okay, but I want to try set theoretical model, not ordered pairs. So what we have to do, we have to go back into this implementation and change that the daughter constituents are defined by a set of two elements x and y. But now if we have everywhere else in the code lines which manipulate the left and right constituents and go directly manipulating the ordered pair, all of this code will stop working because the underlying assumption was changed. Suddenly there is a set and not the ordered pair. And you can see that this way of doing this module or this whole infrastructure will create huge amount of dependencies between different pieces of code and modules, because not only here, but everywhere else the objects we create, the speaker models, lexicon, and whatever post-unitative function, whatever we have, we would always have functions which whose operation presupposes or depends on this assumption that we are using ordered pairs in the phrase structure class. So all of this code will break and stop operating. And not only that, but some of this code is these algorithms that we use elsewhere can be non-trivial and complex. So they make an assumption that we have ordered pairs, and then they do something really complicated things. But if we suddenly have only sets, then all of this logic has to be rethought. Perhaps it doesn't even work. Perhaps what we were doing actually stops working, and this would be clearly the case if we just go and change ordered pairs into sets. So the whole system will break, and not only here, but anywhere else where we have this type of transparent access to the internal properties of our objects. So what do we do instead is that we define here what the daughter constituents are in our technical implementation. Then we provide this abstraction layer where we tell the other external code how we want you to deal with these properties. So we say, please call them left and right, and please don't assume that it's implemented by asymmetric ordered pairs. And now, if I later want to have a set theoretical approach, I can make the change here, and then I can come into these interface functions, and I simply change the implementation. What it now means that we have a left and right constituent, which is of course non-trivial if we have sets. But if we would have a dictionary, for example, then it would be more intuitive immediately how we would define these. Can you see the idea? I only make one change. I do two changes. I change the implementation and then I change the interface, but the rest of the code will still be using the notions right and left. And if all goes well, and most of the cases it of course will, the system should still work. Because we haven't changed how all the other external code is looking at these properties. So I absolutely recommend that when you create the theory of phrase structure, that as you are creating it, that immediately provide this abstraction layer. I mean, before you start to do anything else, before you begin to manipulate them or apply the assembly, the search, derivational search function to your phrase structures. I hope that I was able to explain this idea at least in some level. And then one more comment I do, but this is actually just already, I'm repeating what I already have mentioned, that when you start working with the phrase structure, in the very first steps, after you have created some basic properties and abstractions for them, you need to write a printout function, like I've done here. This is just one example you can start with. A function which is able to print into a file or console at least what kind of phrase structure, what for each object have a method or function that is able to print its contents out into a console or file or wherever you want the print stream to go. So that in this way you have some understanding when you create this object at runtime, what you are creating. So this, I think and hope, was all that I was planning to talk about in this presentation. To summarize, create a phrase structure, create your own dedicated class for the phrase structure. Then define it formally by providing its properties in the init function in Python. And then create the abstraction for these properties create some type of printout function that you can illustrate what you are creating and what these constituents will contain. And in my view, the best way to create complex constituents is allow this init function to take the daughters as input arguments.